Hello everyone, I'm Indika Kumar. I'm from JADS and Tilburg University. In this webinar, I'm going to present use cases of Sodalite Horizon Europe project. Implementation of these use cases are based on the tools or the software developed by the Sodalite project. First, I will briefly introduce Sodalite. Then I will focus on the use cases and their implementation with Sodalite framework. Sodalite aims to resolve the complex problem of application deployment over heterogeneous infrastructures. Nowadays, there are different type of infrastructures which include cloud, high-performance computing environment, edge, fog, and so on. The application should be able to utilize the characteristic of different heterogeneous infrastructure resources. However, deploying application using many heterogeneous infrastructure resources is complex, need a lot of expert knowledge about the resources, their usage, their configuration, and so on. However, typical deployment engineer does not possess such expert knowledge. In order to simplify the deployment of application across heterogeneous infrastructures, Sodalite provides set of tools and the methodology. And within Sodalite, we consider cloud, edge, and high-performance computing infrastructures. Sodalite provide an environment where domain expert and deployment engineers in collaboration can create deployment model. Domain expert who know about the heterogeneous resources and their configuration and how to optimize application for them, they can define those knowledge and make available those knowledge to the deployment engineers. Deployment engineers simply can use those knowledge via the ID provided by Sodalite. So deployment engineer simply design the deployment topology and simply enact the deployment model to create the deployment. This is the Sodalite architecture, which consists of three key layers. First layer is the modeling layer. This layer consists of an ID and knowledge base that contain all the information about resources and resource model and also application model. And domain expert can populate this knowledge base. Also, we have a way to automatically populate some of the knowledge about the resources using platform discovery service. This utility or this service can monitor the infrastructure and extract the knowledge about the resources and populate the knowledge base. With those information, domain expert can also define how to optimize the application component for different hardware. Then the deployment engineer who going to deploy the application can use this information from the knowledge base to create the deployment model needed for the application. Once the deployment model is created via the IDE, deployment engineer can simply deploy the application uh, over heterogeneous infrastructures. Deployment is handled by the uh, infrastructure as a code layer. We have an infrastructure as a code builder which can convert abstract deployment model into concrete executable infrastructure as a code. Here we use Tosca and Ansible. Then also we have some other component to check the quality, for example, bugs, smell, and errors, and also make suggestion to fix them. Executable infrastructure as a code blueprint are used by the orchestrator to provision the resources and deploy the application component. Which orchestrator is the part of the runtime layer. Runtime layer also have several other components to monitor this application as well as to adapt or modify the applications. So refactoring is the component that is responsible for adapting the application. In Sodalite, we have three main use cases, uh, namely snow use case, clinical trial, and vehicle IoT. Snow use case use cloud and HPC resources. Clinical trial use cloud and HPC resources. Vehicle IoT use case use cloud, HPC, and edge resources. Let's start with the snow use case. The goal of this use case is to process images containing snow to predict the water availability. Here we calculate an index called snow index, which indicate the availability of the water on mountain regions. Uh, this is a complex data processing pipeline. Uh, so this is the basic structure of the data pipeline. There are two type of data sources. One come from images created by the users. So there's a crawler that crawl the images from the different image sharing website, and then there's another crawler for webcam images. And the images from the both sources are pre-processed, aggregated, and apply some deep learning model to calculate the snow index. Some component, for example, a skyline extractor, which use a deep learning model, and that model is trained on a HPC infrastructure. Most of other components are deployed on cloud. Uh, Now I'm going to show a demo of this use case. In this demo, I will show the key features of the Sodalite. First is about the security mechanism within the Sodalite framework. Sodalite ID as well as the Sodalite framework is a multi-user framework. In order to securely share the Sodalite framework across different users, we have the role-based access control framework. In the first demo, I will show the that role-based access control framework. Next, I will show the population of the knowledge base using platform discovery service. Next, I will show how to model the application deployment model using our ID and also utilizing content assistance service provided by the knowledge base. There are different type of services, detecting smell, validating the syntax or semantics, visualizing the model, and so on. Then move into deploying, monitoring and redeployment of the application. Let's start with the first one. New team member join to an existing user group, and here we show how to use click clock to create a new user and providing and assigning different role to him. This demo from one of my colleague from Politecnico is Rocio.
In this video, we will show you the process we follow when a new team member joins. This consists of two main steps: creating the user and providing the user with the necessary access roles. This process is managed by Sodalite admins using Keycloak. So to create a new user, we need to go to the Users area and click on Add User button. Here, we compile the necessary user information, for example, the username and the email. We also need to set up his credentials, so we input a password. After this, we also provide him with a default group, the public one in this case. Once this is done, the user is ready to log in from the ID. So we go to Preferences and input his credentials. Suppose that the user has cloned the GitHub repository with the Snow models and tries now to save this abstract application deployment model. He will not be successful, since the semantic reasoner will detect he's not authorized to do so. In order to solve this, we need to include the user in the Snow group that authorizes him to save the AATM models. In other words, we need to add him to the application operation expert groups. This is done in Keycloak. Now, if we ask the user to go back to the ID and try to save the model again, the process will pass the initial authorization phase, and after a few moments, a message will appear indicating that the model was successfully saved in the knowledge base. If the user tries instead to save the resource model, he will get an error message indicating his lack of authorization. So we go back to Keycloak and add him to the Snow Resource Expert group. Now, when he tries to save the Snow Resource model, he will be successful. In this demo, we illustrated the authorization system and its integration with ID. This process will be further refined in the following months.
Okay, let's go to the next demo. In this demo, as I mentioned earlier, we use a platform discovery service to discover the resources. In this case, OpenStack virtual machine in the test bed. Platform discovery service can automatically extract the information from this infrastructure, for example, number of virtual machine and their configuration, and it can then populate the knowledge base with those information. We can trigger the platform discovery service using ID. The populated knowledge about the resources can be used to the modify an existing abstract application deployment model. Here AADM mean abstract application deployment model, the deployment model created by the Sodalite ID. Let's go to that video. This demo is from our Sodalite partner Atos. Josu is the presenter and he's the one responsible for the ID.
A member of the node use case wants to take one of the existing models previously produced by other members of the team. So let's assume that I want to open a new view, and this view is the knowledge base browser view that supports to browse all the existing models that are already in the knowledge base. So at this moment, the knowledge base is being requested to collect all the existing models, and this is a process that is going on the background, so the user is not blocked and can still working on the ID. So it will take a while to retrieve all the models. Now they are already rendered in the view, and they are classified in resource models and the abstract application deployment models. But now we are interested in our abstract application deployment model. So let's consider that the user is interested in retrieving the model, and the user can go and retrieve the model. For that, it has to select a folder within the local workspace, and the model is retrieved. The model is now available in the knowledge base, in the local workspace and in the ID, and the user can start working on the model in order to improve it, fix any issue, or just extend it, adding more components. At any time, the user can also request to refresh this view. Periodically can pull for new models. For every model, the user, in case that the user has write permissions, can also delete the model, delete any model in the knowledge base.
Next, I'm going to demonstrate the usage of ID. Uh, there are several demos showing different features of the ID. Sodalite ID is an Eclipse plugin. You can install Sodalite ID plugin to your Eclipse. Uh, you can find the more information about how to install the Sodalite ID in our website. Here we show how to retrieve the knowledge from the knowledge base. The knowledge include both resource model and application model. The application deployment models RM mean resource model. This include the information about different type of resources, Docker, HPC, OpenStack, and so on. AADM mean application deployment model. There are deployment model for different use cases. Here we can open existing deployment model and then we can modify that. Now I will use a separate video to demonstrate how to use ID to create AADM as well as edit an existing ADM by utilizing the assistance provided by the knowledge base. This video from my colleague Joshua from Atos. He's the person, he's the developer responsible for the ID.
Okay, let's start by creating a new Node component within this Node deployment topology model. So first we create a Node component for MySQL, and I will use Content Assistant in order to understand what are the modeling entities that I need to set up to describe these components. I will start by providing the type, and using Content Assistant I can get the types available in the knowledge base. I will select the price component, and I will then go through describing the different properties. So by using Content Assistant I can also retrieve from the knowledge base the existing properties defined within Dockerized component, and I will provide the image name, and then I will go through requirements, and I will provide some other requirement which has been defined for the Dockerized component. So I will provide the registry and the network requirements. So I have to specify what will be the network node, and for that I can also use the inference capabilities of the knowledge base in order to search and find nodes that can satisfy this requirement within those which are already in the knowledge base, or also the ID can inspect the local model in order to find them as well, in case that they are not found in the knowledge base. So similarly for the registry, I can describe the node, and I can try to find the nodes in those which are available. So here I'm going to select this one. Okay, so let's assume that once that I have the requirements specified, I can also come back to the properties, and I can try to determine what is the network name. But in this case I will get this property from an existing property somewhere in this description. I mean, it's not MySQL, where I can try to determine where I can find this property, and I will try to find the property in the network entity, and the property in the network entity will be name. So in this way I can also create properties which are taken from other places.
Our Sodalite ID is a multi-view modeling environment. In the next video, Josh will explain the different type of views available in the ID.
The ID supports different ways to visualize the application deployment models. The main editor is the textual one, and we have also a visual representation and an outline representation, which is a tree-based representation in case that we are visualizing textual model. where we can see and we can go through the textual editor through the outline in an easy way, so we can have a look and see what are the different components of the application, and we can inspect the component description in the textual editor in an easy way. For the visual representation, which can be generated automatically out of the model, out of the textual representation, we can also have an outline, and with the outline we can go through the model and to inspect the different components and the dependencies between these components. Every element in the visual representation can be partially modified. I mean, most of the properties are editable through the associated form, which is available in the properties view by just clicking on the component, and the property view is associated at the form that provides the different properties is included. So for instance, we can modify the property of the registered certificate, and once that we have selected a new different type, this is reflected into the graphical representation. Similarly, for instance, we can select what is the input, where we can take a particular property, or we can modify as well dependencies or the requirements between components. So here we can select a different host for this component, and that will be reflected into the model. All those changes introduced in the visual representation are automatically, upon saving, provided to the other representation, to the textual representation and the associated outline.
Next, I will present some of the key features provided by the semantic reasoning engine.
Once that we are done with the description of this new component, and we think that the entire model is complete, we can save the model into the knowledge base. So when we trigger the saving, the knowledge base receives the model and store the model. This process takes a while. In this case, the model could not be saved because there were issues detected, and the user is prompted to fix them. Issues are spotted into the model close to the entity that is being affected. So here we are notified that this is a required property registry URL which has been set for this concrete component. And in some cases, we also get a quick fix that can be applied by clicking on the suggested fix. The model provides a new property that is missed, and then we have to provide a value. We can just provide a fixed value, a literal, or we can also use the get input and use content assistant in order to get Docker registry URL. So once that we save and fix the issue, we can try again to save the model. In this case, the model was saved successfully, and the user is notified with the URI of the saved model. However, during this validation, some recommendation has been returned, and they are shown to the user at the point in which they can be applied. So here we have some suggestions in order to include some requirements, particularly the requirement host, and we get some recommendation in order to fulfill or satisfy the requirement. So similarly, we can just get different quick fixes that can satisfy this warning. I mean, can provide this recommendation. And for instance, we can select one of those quick fixes in order to inject a requirement host that is referencing this concrete node. So if we do that, the host requirement is being added to the component description. And once saved, so we release the warning.
Next, we will see the demo of Ismail detection using semantic reasoning. Uh, Video is from Soy, it's a colleague from CERT.
Now I will save the model. The saving is in progress. The model will be saved successfully, and the smells will be returned as warnings to the user. The model has been saved successfully, and here we see the first smell that has been detected about an invalid IP address, because here it is an unrestricted IP address permitting all the incoming packets to be accepted from all the IP addresses. Also here we have two warnings returned about the username property. We have a hard-coded secret smell because the username value has been hard-coded. Also, we have a default user that is admin, that is, in this case, sorry, it is root, as we see here. And also the fourth smell, it is about the exposed ports that is in invalid port range, because TCP port values should be within the range from 0 to 65535. By the detected smells, we have less error-prone application deployment models.
After this step, we will have a defect and error-free deployment model. So we can go to the next stage to where we deploy the application. We can deploy the application from the IDE. We can right click on the application deployment model. There's a menu item to deploy. We need to provide several configuration parameters. Most of these are input to the deployment model. For example, information about the Docker registry, virtual machine, type, MySQL database, password and username, and so on. There are some information related to the orchestration process. For example, we can configure number of orchestrator workers so that we can configure or exploit the parallel execution of the deployment process. Instead of defining the inputs in this form, we can also define inputs in a file and then browse that file using the select option. Input YAML file, it contains input. So from that file, here we automatically populate all the fields. You can see the deployment progress. Once the application is deployed, we can monitor the application and the infrastructure. Next demo is about that. Uh, we have a Grafana dashboard integrated into the IDE. With that dashboard, we can see the resource usage, and also we can define the alerting rule in using Prometheus Alert Manager. These alert can be based on the metrics collected by the monitoring system. Let's check the demo. This demo from Jesus. He's also from Atos. He's responsible for the monitoring system.
Hello, I'm going to explain the status of Sodalite's monitoring system at the end of year 2, and to demonstrate it, I will focus on the Snow use case deployment. First, let's take a look at the different monitoring components and how they interact with each other. In the Sodalite stack, and only deployed once, there is the monitoring core, made up of these 5 services. Prometheus is the main one, logging, serving, and collecting metrics. Grafana is used to display the metrics to the user in a pleasant way. Every application may deploy with it different exporters. In Sodalite, applications are deployed and undeployed constantly. We need a way to register their exporters with Prometheus dynamically. Since Prometheus doesn't allow this out of the box, we're using an instance of console as a middleman. Exporters are registered on console automatically when they are deployed, and Prometheus picks them up from there. Users may state some refactoring rules that they want their application to observe. In order to allow this, we are creating a rule server that exposes a REST API. When the application is deployed, their monitoring rules are sent to the server, which registers them with Prometheus. The alert manager is responsible to send these alerts to the proper recipient, in this case the refactoring engine. Let's proceed with the demo itself. The Snow application has been deployed some minutes ago. It is made up of 2 virtual machines. On each VM, a node exporter is automatically launched and registered with console. Here are the 2 node exporters that have been launched in the 2 Snow VMs and the metrics that they are exposing. As we can see, we can connect directly to the virtual machines and see the raw data. In console, we can see that the exporters have been correctly registered. Here we see all the services organized by type, and here we see the 2 Snow virtual machine node exporters. This is another test exporter that we have in another virtual machine. And if we go to Prometheus on the targets that it's picking the metrics from, we can see that they are correctly being picked up. In this case, we will focus on the node exporters that are being used by the Snow application. In Prometheus, using PromQL, we can query some data to check metrics. In here, for example, if we write this, we can find out the average CPU load on the different instances of the virtual machines. Still, this is very tedious for the user, so we have created a dashboard for node exporters on Grafana to view all the relevant data at a glance. Here we can see a summary of all the virtual machines that are being monitored by node exporters. These 2 are the ones for Snow, the first one and the third one. These are average metrics for all the virtual machines, and here are the metrics corresponding to the selected virtual machine. This virtual machine can be selected up here. All the data is refreshed every 15 seconds, but that can be changed. And as we can see, it's very comprehensive. We can see CPU usage, memory, network bandwidth, disk space used, etc. As for the alerts, when the application is deployed, they are automatically registered with Prometheus through the rule server. We can see the alerts for the Snow use case here. When the disk is running low on free space, this alert is activated and arrives at the refactorer. which triggers an action. For example, it increases the disk on this virtual machine. We also have an alert that activates when the majority of the cores are under heavy load, which prompts the refactorer to increase the number of cores on this VM, and an alert that notifies the user when the data received by the virtual machine in the last hour is less than 30 megabytes. This signals the virtual machine is not receiving images from the cameras. All these services are deployed automatically when the user deploys the application. Aside from their application requirements, they only have to provide the rules they want their application to observe. Here we can see an example of the input file needed for the alerts. Next year, we will work on simplifying the data the users need to give to generate the alerts, as well as continue development on other components like the HPC exporter.
In response to the alert generated by the monitoring layer, refactoring support in the Sodalite may decide to adapt the application deployment and redeploy the new deployment. Next video is about refactoring support. It shows switching between two alternative deployment in response to alert related to CPU usage.
In this demo, we show switching between deployment variants in response to resource usage alerts. We consider two deployment variants for the Snow application, 2 nodes and 1 node. If the CPU usage in the host node is low, the default 2 nodes deployment is moved to the 1 node deployment. When the CPU usage becomes high, the 1 node deployment is refactored back to the 2 node deployment. Here, show the refactoring decisions in our event-driven policy language. The first rule implements switching from the 2 nodes deployment to the 1 node deployment. The Snow VM2 and other relevant components are removed from the deployment model. The modified deployment model is enacted using the orchestrator API. The second rule implements switching from the 1 node deployment to 2 nodes deployment. Using the knowledge base and semantic matchmaking, the necessary VM node and its dependent nodes are discovered, and the deployment model is updated accordingly. Let us see the refactoring in action. Here, you can see the deployment refactor and the orchestrator API at our testbed. At the end of the deployment pipeline, the refactorer receives the information about the initial deployment from the IDE. Information includes AADM URI and inputs file. We can check the status of a deployment using the API of the orchestrator. Here, you can see 2 Snow virtual machines. Let us consider switching to the 1 node deployment. Refactorer received the low CPU alert. Switching to the 1 node deployment is triggered. We can check the status of the redeployment. As you can see, the deployment now only have a single Snow virtual machine. And the operation is update. After a few minutes, the update operation was successful, completing moving to 1 node deployment. Now, let us consider switching back to the 2 nodes deployment. Refactorer received high CPU usage alert, and the relevant rule was executed, which triggered switching the 1 node deployment back to the 2 nodes deployment. We can check the redeployment status. After a few minutes, the update operation was successful, completing moving to 2 nodes deployment. You can see 2 Snow virtual machines and Docker hosts.
Refactoring video concludes the demonstration of the Snow use case and its implementation using Sodalite toolset. Now we can move into the next use case, clinical trial use case. Clinical trial use case aim to simulate a real physical clinical trial by means of simulation. Uh, date Clinical trial pipeline is again a big data processing pipeline. Process mostly images. Some of these components of the pipeline are deployed and executed on HPC. Few components are executed on cloud. Uh, Clinical trial use case also use most of the tools from Sodalite, especially modeling and deployment tools. With the Snow use case, we have already saw the features of the Sodalite ID. So I will only show the deployment. There are three type of deployments for this use case. One is using Tor resource manager for high performance computing. Other one is using Slum, again it's for high performance computing. Then we have a hybrid deployment environment where we use Amazon Amazon EC2 as well as Tor resource manager. Tor cluster is in the Sodalite testbed, Slum testbed also from HLRS. In the third deployment, as you can see here, some of the components are deployed on Amazon EC2. Then there are some other component are deployed on Tor cluster on our test bed. Let's see the deployment of this. Uh, Clinical trial use case is from HLRS, University of Stuttgart High Performance Computing Center. This demo is from Kamil. Here we assume that the abstract deployment model for the clinical trial use case has been created using Sodalite ID. We will focus only on the deployment process. We need to provide the input required by the deployment. You can see some of the inputs are related to Amazon access account. Then there are some related to orchestrator. Then also we will have to provide some firewall and security rules. Then we can simply deploy. We can see the deployment progress in the ID. There's no virtual machine in the Amazon EC2 dashboard. You will notice now uh, creation of the new VM within few seconds. You will notice. Yes, this virtual machine is created by our orchestrator based on the information in the deployment model. Some component will be deployed and executed on this virtual machine. Now we can see the what is inside this virtual machine. Here there are two windows. One window show the virtual machine, other window show the Tor cluster, because our application will be deployed on both, so we can see the progress. This one is the Amazon. This is the uh, Tor cluster in at the HLRS. You can see the progress of installing software. Uh, all are done by the orchestrator. Orchestrator create the virtual machine, deploy the component, install the necessary software, and so on. Singularity is a container runtime for high performance computing. It's similar to Docker, but for the high performance computing. Now the component has been deployed. Now they are executed. So they produce data and consume data. Yeah, different script needed for different component are created. One script has been executed and it produce some result. Now here data from Amazon component in the Amazon VM is moved to uh, the PBS cluster at the HLRS via grid FTP. Now new job is created at the PBS cluster. We can see the progress of that job. Job has finished. Status is C, mean completed. Now the output produced by that component is moved from PBS cluster to Amazon VM. These are the file received by Amazon VM. Now, next job will be executed at the Amazon virtual machine using those input data. ID can see here the deployment was successful. ID from the ID user can see the status of the deployment. We can also check the what is inside each script. This simply execute a container image with some input data. This is also similar. Use some data and execute job in the container. This is a job executed on the PBS talk cluster. Again, use singularity. All are shell script. Uh, Clinical trial workflow has been completed. We are just observing the result produced by the workflow and also the sum of the component. Next use case is the vehicle IoT use case. This use case provides set of value-added services to the drivers. These services include license plate detection, reverse geocoding, risk scoring, intrusion detection, drowsiness detection, and so on. Some of these services are deployed on edge node, edge gateways. Other are deployed on cloud. Some of services use machine learning model, deep learning model. These deep learning model are trained using high performance computing resources. So in some, this use case use cloud, edge, and HPC resources. Complete use case is very complex, so we will only focus on a small part of the use case. Uh, in this demo, we will show application of refactoring at the vehicle IoT use case. Whenever GPU resources are available, the services should be able to utilize the GPU resources. In order to do that, we have to undeploy the services and redeploy the services using GPU resources. Uh, this is the scenario. We have two type of scoring services, GPU version and CPU version. Uh, and then based on the resource availability, we have to use the correct service. This is the architecture of this system. We have all these components now from Sodalite. Uh, we have a edge test bed that include the edge gateway, which include the GPU and CPU resources. These services are deployed on this test bed, and we use Kubernetes distribution for the edge. In the knowledge base, we have all the information about available resources as well as the component. And these resources or changes to those resources can be automatically discovered using the platform discovery service. Uh, Also, we have a component from the use case called node label monitor, which can monitor the changes to the resources and generate the alerts. The refactorer can receive these alert, and based on the alert and also based on the information available in this knowledge base, refactorer can identify alternative deployment, and then refactorer can redeploy the application using the identify the alternative deployment via the orchestrator. Uh, Demo include 4 steps. Here we will start with the deployment of the application from the ID. Then we consider monitoring of the edge cluster and the execution of the platform discovery service and knowledge base population, and then dynamic refactoring. This demo is from Adapton. Paul is the presenter.
By examining the list of installed Helm charts, we can see the chart that has been installed by the orchestrator. And by looking at this in detail, we can see specifically the node selector terms that have been applied as a result of the ADM specification. Switching back to the IDE, and knowing that our target node happens to have a GPU resource available, we can manually patch the Helm chart to deploy a GPU-optimized version of the application to demonstrate the redeployment functionality. Under the Sodalite system, this is handled automatically by the refactorer, but we do this manually here in order to exemplify the kind of runtime adaptation that is carried out by refactoring. The application has now been successfully redeployed by patching the existing Helm chart that runs within the cluster, which we can now go and look at in more detail. As in the previous case, we can see that the deployment has been created, and we can verify the adaptation by querying the underlying container image. Here we see that the pod is now running the GPU-optimized version of the application container, which itself is a layered version of the application on top of the CUDA runtime. This is generated as an image variant by the Sodalite image builder. Furthermore, by examining the values of the deployed Helm chart, we can also see that the additional key value pairs specified in the AADM for the GPU specification have been successfully propagated. Now when we look into the logs of the application itself, we can see that the application is now running with the GPU optimizations enabled. In the next video, we will look at the functionality of the Kubernetes node label monitor and its interaction with the Sodalite platform discovery service and knowledge base.
Next, we will show the monitoring of the Kubernetes cluster and also use of the platform discovery service to discover the edge resources and populate the knowledge base.
The Kubernetes Node Label Monitor is a custom Kubernetes controller developed within the Sodalite project for monitoring nodes within a Kubernetes cluster and relaying information about changes to node labels and annotations to the Sodalite Platform Discovery Service. The Platform Discovery Service is, in turn, responsible for generating a Tosca representation of the cluster state and updating the knowledge base. When the label monitor is first installed into the cluster, it discovers all of the active nodes and their respective metadata and sends this to the Platform Discovery Service via REST API endpoint. This provides the initial population of the knowledge base. Information about specific accelerators, such as available GPUs, can then be queried directly from the knowledge base. When GPU resources are added or become available for a given node, these are reflected either via changes to node labels or annotations by the respective device plugin. By manually labeling the node as GPU capable, we can simulate the work done by the GPU device plugin. Once the label is applied, the flow from label monitor to platform discovery service to knowledge base can be observed, with the knowledge base now reflecting the updated node state. Through the combination of the node label monitor and the platform discovery service, it is possible to keep the knowledge base synchronized with the active cluster and its available resources. This information can then be drawn on directly by other Sodalite components, such as the refactor or the IDE. In the next video, we will look at how the Sodalite refactor is informed by the Kubernetes node label monitor through the Sodalite platform discovery service in order to provide runtime refactoring in response to dynamic changes in node state.
Next, we are going to demonstrate the GPU refactoring.
Using our default Helm chart installation from earlier, we can see that the currently deployed version of the application is running entirely on the CPU. The addition of a node label signifying the availability of a GPU is carried out on the named node. This triggers a notification by the Kubernetes node label monitor to the Sodalite platform discovery service, which subsequently updates the knowledge base. As the GPU becomes available, the refactor receives a notification from the platform discovery service and then queries the updated state from the knowledge base. In the case where GPU has become available, the Helm chart values tied to the ADM are patched automatically, and the deployment within the cluster is updated. By examining the output of the refactor, we can see that the notification has been received from the platform discovery service and that the GPU available rule has been matched and executed. The refactor then calls out to the orchestrator to apply the update into the cluster. Now when we go back and check on the current state of the deployment, we can see that the deployment has been dynamically reconfigured and is now making use of the GPU.
In this webinar, we have provided an overview of the Sodalite and also provided detailed demonstration of the use case implementation using the Sodalite platform.